Okay, so let's get started. So the second lecture is going to be based on wireless transmission, and as I told you last week, it's based on Chapter 2 and some other references that I've provided for you on UTS Online. So we're going to start from scratch. So some of you might know some of these things. So please bear with us until we get to some more interesting stuff towards the end of the lecture. Okay, now when we talk about wireless communication, you've got communication that can take place from very low frequencies up to extremely high frequencies. So we have these bands called VLF. Riyaj, you want to come back later? You've got very low frequencies, medium frequencies, high frequencies, and so forth. So as we move from very low frequencies to extremely high frequencies, a lot of things change. First of all, one of the important things is the wavelength. Okay, so when we are looking at something like of the order of gigahertz, the wavelength, remember there's a relationship between wavelength and frequency, which you might have done at high school physics. They're related by this expression here. Okay, wavelength is velocity of light divided by the frequency. So as we go higher and higher into higher frequency bands, the wavelength gets smaller and smaller. Now the implication of this has a number of implications. First of all, the antenna size that we use is approximately proportional to half the wavelength. So as we go into high and higher frequency bands, the size of the antenna will decrease, which is a big plus in wireless communication, because you want your antennas as small as possible, especially for mobile devices. But the other thing that happens is, as you go into high and high frequency bands, the propagation loss, which is the loss that takes place between the transmitter and the receiver, also increases very rapidly. So to cope with that, you've got to have much better antennas and so forth. The other thing that has been taking place is over a period of time, initially most of the, when wireless started, most of the communication was on this side of the spectrum, and as slowly we moved to medium frequency and then to high frequency and then to VHF and so forth. So over a period of time, we have developed technology that enabled us to move further into the frequency band. So one of the things that happens is that the lower frequency bands are getting more and more congested, and as they get more and more congested, there is no more space available in the lower frequency band, and consequently we have been pushed into high frequency bands. And now as time goes on, we'll find out maybe even the UHF band is almost congested. Now we are moving into the SHF band, and from the SHF band we'll eventually have to move to the EHF bands. So there are good things, positive things, because if you look at it, as you move to higher and higher frequency band, for example, if you have 30 gigahertz, if you take even 0.1% or even 1% of the bandwidth at 30 gigahertz, we're looking at about 3 gigahertz bandwidth, which is a very large bandwidth. Whereas if you take 1% at a lower frequency, like 30 kilohertz, it only gives us about say something like 0.3 hertz. So as we move to high and high frequency band, the amount of bandwidth that is available also increases. So as I said, there are some pros and cons associated with moving to high frequency bands. The pros being that your antenna sizes are getting smaller, and the antenna gains consequently also rise, but the propagation loss, atmospheric losses, all of those increase as we move on to higher frequency bands. Now, the other thing that also happens is as we move to higher and higher frequency band, the propagation mechanism also changes. So, for example, at low frequency bands, electromagnetic waves can travel along the surface of the Earth as surface waves. So we can go well beyond the horizon using at low frequency bands. Whereas as we move to higher and higher frequency bands, we need a line of sight path between the transmitter and the receiver for communication to take place. So this is probably a disadvantage because over the horizon, if you put towers, you'll notice that when you drive on a road out of Sydney, you see on top of mountains there are towers, and those towers have microwave links. So you will see approximately every 60 kilometers or so, you will see towers so that a line of sight path can be established. So there is a need to place repeaters if you want to build a line of sight path along the surface of the Earth because of the fact that the Earth's surface is curved. Okay, now there are two terms, spectrum and bandwidth. Okay, and people use these two terms quite wrongly sometimes because spectrum refers to a range of frequencies. For example, this red blob that you see here, the spectrum is from 902 to 902.2 megahertz. Okay, this might represent a carrier in a GSM system, whereas the bandwidth of this would be something like 200 kilohertz. So the difference between the upper frequency and the lower frequency is referred to as a bandwidth, whereas the spectrum refers to a range of frequencies. Usually, to describe radio communication in terms of spectrum is more accurate because you are establishing what is the lowest frequency and the highest frequency in that process. So I expect you to know the difference between these two terms. On this table on the next slide, there's a whole bunch of frequencies that are used for different applications. Now, I've put a note here that I don't expect you to memorize these frequencies because that's not the purpose of this subject. So you can see that, for example, if you look at mobile telephony, in the Nordic mobile telephony system started in the VHF bands, and as these bands became more and more congested, the higher bands, almost moving into the UHF bands, started being used. So, and as the 900 megahertz bands got congested, the 1800 bands were used. Okay, so over a period of time, the lower frequency bands got congested, and we were forced to move to higher frequency bands. And obviously, the technology for higher frequency bands are being continuously developed. Okay, a little bit introduction to signals. Again, this is something that you would have seen at some stage in earlier life. Any signal can be represented in this form here. Okay, this I'm referring to this thing right at the bottom of the slide. Okay, you've all seen this representation of a signal at some stage. So what does A represent? And F represents? And phi represents? Phase. Okay, so A represents amplitude, F represents frequency, and phi represents phase. Now, these are the three important properties of a signal, and these are the properties of a signal that are modified in any form of transmission. So, for example, if you're modulating a signal with a carrier wave, you either modulate its amplitude, or you modulate its frequency, or you modulate its phase. Okay, so modulation, multiplexing, multi-access, even diversity to some extent use these properties of a signal. Now, you probably would have also come across a Fourier representation of a periodic signal. Any signal, if you've done a subject in signal theory at some stage in your life, you know that any signal, any periodic signal can be represented as what? As a sine wave, as one sine wave? Okay, as a sum of a number of sine waves, each sine wave having a different frequency, okay, and each one having a different amplitude. Okay, so that's what this graph is trying to tell you, that you can take any periodic signal and represent it as a sum of sine waves. The sine wave with the lowest frequency is called the fundamental component, and then there are other components. Each one of these, the red one, the yellow one, the green one, they all represent sine waves of different frequencies and different amplitude. If you sum all of these up, you will get a periodic signal. Now, the implication of this is that ideally speaking, if you take a periodic signal, it will have an infinite number of frequency components. So essentially it means that you have a large number of frequency components. So the spectrum of an ideal periodic signal would have an infinite number of components, and when you transmit it through a band limited channel, some of the components will be truncated. So at the receiver, what you'll end up will be a truncated version of this ideal periodic signal. Now, in the when we represent signals, it could be in the wireless domain or in the wired domain, we use three important domains to represent a signal. The first domain is called the amplitude domain. So in the amplitude domain, you've got a variation of amplitude versus time. So here you've got a sinusoidal signal in the amplitude domain. Amplitude as a function of time. The second and more important representation of a signal is the frequency domain. In the frequency domain, you have amplitude on the y-axis, and on the x-axis you've got frequency components. So for example, for this signal, this could represent a single sine wave which has a specific frequency and an amplitude amounting to that much. So whereas a pure sine wave could go up to infinity in the amplitude domain, in the frequency domain, it is just represented as a single line corresponding to that particular frequency. Okay, so for example, the diagram that I showed you earlier to show the difference between a spectrum and bandwidth is a frequency spectrum representation of a signal. The third representation that is used quite often in representing a signal is called the phase domain. And in the phase domain, you have what is referred to as I and Q axis, and a sinusoidal signal is represented as a rotating phasor. Okay, and the phase is usually measured with the positive I-axis. Okay, so later on, when we start looking at modulation, different modulation techniques, we'll see what the phase domain of different digital modulation techniques look like. The next bit of revision is on antennas. Okay, so an antenna is an important component in any wireless system because an antenna is the transition from a wired to a wireless media. So essentially, whenever an electrical signal that is produced has to be transmitted as an electromagnetic wave, so the antenna is the one that converts it from an electrical to an electromagnetic signal. So you have a transmitter. Antennas are capable of doing both. Okay, they're capable of converting an electric signal to an electromagnetic signal, and also at a receiver it will collect the electromagnetic signal and convert it to an electrical signal. And you can use the same antenna to do both the functions. Now, as I said earlier, the size of an antenna is approximately between quarter of wavelength and half a wavelength. So, and this is the minimum size of an antenna. That's why I said as we move to higher and higher frequencies, if you look at the older mobile phones, they used to have a long antenna sticking out of them. Nowadays, if you look at mobile phones, you can't even see the antenna because it's built within the device. It's much smaller in size. Now, the gain of an antenna is dependent on two things. One thing is the size of the antenna, okay? So the larger the size of the antenna, the larger the gain. And as we'll see later, the gain of the antenna is also inversely proportional to the wavelength of the antenna. There are many different types of antennas, monopole, Yagi, horn, parabolic, helical, microstrip, and so forth. I'll show you pictures of some of these later on. Now, in terms of antennas, an antenna is a device that propagates electromagnetic waves. Sometimes an antenna propagates electromagnetic signals equally in all directions, okay? And those are referred to as omnidirectional antennas. For example, antennas that you have on top of radio masts or TV masts, or even most wireless LANs that are in the middle of an area, they are required to sort of propagate electromagnetic wave equally in all directions. The second type of antennas are referred to as directional antennas. These antennas are antennas that radiate power in one specific direction. Okay, now whenever we take measurements about an antenna, all these measurements, for example, the gain of an antenna is usually expressed as dBIs. Okay, now the I refers to an isotropic antenna. An isotropic antenna is a theoretical antenna. It doesn't exist in practice. And it's an antenna that is a point source, a point in space that emits power equally in all directions. Okay, so if you look at it, its radiation pattern is like a sphere because it emits power equally in all directions. Now, an isotropic antenna is not a practical antenna because it's impossible to construct an antenna that is an isotropic antenna. But in terms of comparison, in terms of comparing it with other antennas, it provides a good reference. So this is why whenever you see the gain of an antenna, you'll always see dBs and then a letter I at the end of it, and the I refers to an isotropic antenna. Okay, now I just mentioned the word radiation pattern, but I haven't told you what it is. The radiation pattern is a pattern that shows the way and the power that is radiated by an antenna looks like. Okay, now I don't know if do you want to just pass this to the back? Okay. Those of you who didn't pick that up at the beginning. Okay, now these are the diagrams that you have there are some practical antennas. Okay, I've just taken them from a catalog. Now, if you look, there are two antennas. The first one is an omnidirectional antenna. Okay, and the second antenna. Did everybody get a copy of that? Still waiting. If you have excess copies, can you pass it this way, please? Any more copies left? Okay, so if you look at that diagram there, on one side you will see an omnidirectional antenna, and on the other side you have a directional antenna, a sectored antenna. Okay. Now, I think for the omnidirectional antenna, they have drawn a radiation pattern. Okay. If you look below the picture of the antenna, there is a diagram which shows in sort of a 360-degree plot how power is radiated by the antenna. So if you look on the horizontal plane of that antenna, you see that power is dissipated equally in all directions from that antenna. Okay, whereas the first diagram is more on the vertical plane, and it shows a kind of a elliptical radiation pattern, saying that most of the power is if you look on the vertical axis, which is the axis that I'm standing in, most of the power is radiated within an angle, and the angle is actually specified earlier up. If you look in the specifications of this antenna, it has antenna type, frequency, the impedance, the connector that you use, what is the maximum power it will radiate. So this one has a 10 watt, and then it has a gain, and if you look at the gain of that omnidirectional antenna, it says 8 dBi. Okay, so the I there refers to an isotropic antenna, with respect to an isotropic antenna. And if you look at the half power beam width, okay, so this is the width of the beam that an antenna creates. So in the horizontal plane, it's 360 degrees because it sort of radiates power equally in all directions. But on the vertical plane, it says 13 degrees. So within an angle of 13 degrees, it emits all the power in a vertical plane. Okay, so if you wanna, this radiation pattern will be very much similar to something like a donut. Okay, if you look at a donut, if you do a cross section horizontally, you'll get a circle. But if you take a cross section vertically, you'll get a sort of an elliptical pattern. Okay, so that's some practical this thing. This is something that sometimes when you are a planning engineer and you're designing a system and you have to choose an antenna that you're going to use for your transmitter and receiver, you will go through specs like this to try and find an antenna that is suitable for the task that you want to do. So two things that we talked about were the radiation pattern, which is a graphical representation of the radiation properties of an antenna. Okay, and usually because we can't display things in 3D on paper, we usually have a XY plot and a YZ plot and a ZX plot. Okay, so usually you will find the radiation pattern of an antenna drawn in three different diagrams, each showing the radiation in a specific plane. The other thing that we talked about is the beam width, or sometimes also referred to as the half power beam width, and that is an indication of the directivity of an antenna. Okay, so if you've got a beam width of 360 degrees, it means you're dissipating power equally in all directions. If you've got a beam width of 13 degrees, which is a very small angle, you've got a very directive antenna. So if you've got an antenna that has a very small beam width both in the vertical plane as well as in the horizontal plane, that means it is emitting its electromagnetic energy in a very confined area. And those are the antennas that you will see on top of masts in point-to-point links that you're trying to establish between two cities. You will find highly directional antennas being used. Okay, so we've talked about the concept of a radiation pattern and how what is meant by the beam width. Now, the gain of an antenna, okay, if you look at the last term that is given here, the gain of an antenna is defined as the maximum power in the direction of the main load compared to the power of an isotropic radiator with the same average power. Okay, so this is how the gain of an antenna is measured. It's the gain in the direction of the main lobe, okay, with respect to an isotropic antenna. Okay, so here is an example of two different concepts. One is a directed antenna. So here we've got a directed antenna. This is how the radiation pattern of a directed antenna will look out. Now remember, I told you that when because the antenna, the radiation pattern is a three-dimensional concept, you've got to have a XY, a YZ, and a ZX diagram to completely illustrate how the radiation pattern of an antenna looks like, and this is what you have here. And as you can see, by looking at these three diagrams, you can see that the radiation of this particular antenna is highly directional. If you look at the side view as well as the top view, you can see that most of the energy is traveling in one specific direction. Okay, so this is a directed antenna. Now sometimes, especially in cellular communication, you might have a number of these directed antennas placed. For example, in this case here, we have 3 of these directed antennas that have been placed in such a way that you can get 360-degree coverage. Okay, so for example, if you look at this diagram here, you have one antenna pointing in this direction here, you've got a second antenna in this direction here, and you've got a third antenna in this direction here. And each one of these antennas is a directed antenna, okay, and because it's a directed antenna and maybe it has a coverage of about 120 degrees in this case, you can get a 360-degree coverage, because even in mobile communication, your mobile user can be anywhere within a 360-degree angle from the base station. So now the question you might ask is, why are you using these kind of directed antennas? Why not use an omnidirectional antenna? What would be the reason for that? Sorry?
Reception will be stronger.
Yes. Why? But why specifically? The what? No, it's not. No, I'm asking you is, why are we using 3 directed antennas instead of using an omnidirectional antenna? So gain. Okay, you can get a much higher gain using directed antennas. Okay, so because you get a much higher gain using directed antenna, if you look at the 2 antennas that you have on the diagram, you see that one is a directed antenna and the other one is an omnidirectional. And if you look at the gains, there's a big difference. So you can get much higher gains using directed antennas that have been placed at 120, or in this case here, in the second case here, you've got 6 antennas that have been placed in such a way so that you can get an omnidirectional coverage but with a higher gain. So these are referred to as sectorized antennas. Okay, now remember I told you earlier that as time went on, you can see the heights of antennas have decreased considerably. With the early mobile telephones were referred to as bricks, because they were almost a size of a brick and a big antenna sticking out of them. And then as time went on, the antennas have become smaller, and nowadays you've got helical antennas that are within mobile phones. If you look at a base station, if you look at a mast of a base station, you will find these antennas which are referred to as panel antennas. Now, one of the specifications I've given you on that sheet of paper is for a panel antenna. So it's the directional antenna is a panel antenna, and it has been put up here. Okay, and sometimes you might have on the same antenna maybe a panel antenna for UMTS and maybe another panel antenna for a GSM 900 and so forth. Okay, so this is how on the next slide you see how you could have 3 sets of antennas. Okay, there's 2 here and there's 1 behind, and these are used to achieve a 360-degree coverage. Okay, and so this is how practically, if you those of you who might have actually climbed up one of these masts and done some wiring on this, these masts are probably not that bad, but some of the other ones can be pretty horrific to climb up and do some wiring on it. I used to do that. Probably that was the first thing I did when I graduated many years ago. And sometimes if you climb one of these 100-meter masts, they even sway for the wind. So it goes like that, and you try to not to look down, you know, and carry on doing the work. Okay, so as I said, on one mast you can have many antennas working together, and it's also possible for different operators to share a site. Okay, so maybe one site might be a Telstra site, but other operators could also be sharing the equipment that is on that site, because as time has gone by, especially in developed countries, these antennas, these masts are becoming a sore site, and people don't like, the councils don't like these masts being put up in their vicinity. So as a result, more and more sharing of these sites has come about. You'll also find on top of buildings, when you come by train to the city, if you look up on the top of buildings, you'll see antennas placed, and trying to achieve coverage by placing antennas on the top of buildings. Okay, now mathematically, the gain of an antenna is given by this equation here. The gain of an antenna is 4 pi AE, where A is the effective area of the antenna divided by lambda squared. And in this formula, you can replace the lambda by the wavelength and by the frequency and the speed of light. Okay, now the other antenna that you'll see used quite often, especially point-to-point links, even on mobile base stations, if you look slightly below the antennas on the top, you will find a parabolic dish. Okay, and parabolic dish are used to provide point-to-point links for communication. Maybe you from one single point you want to communicate with a number of base stations, and these base stations might be connected back to the central station using point-to-point links. So parabolic antennas have a very good property. Does anybody know what is the property of a parabolic antenna that has made it quite useful? Sorry, focus, yeah, and more about it. So what does it mean? Directional. It's directional, yes. Parabolic antennas are very directional. That's true. The other thing that you will notice is because of the equation that's associated with the surface of the parabola, if you put a source here, okay, the wave that is produced by a parabola will be planar. That means it will produce almost perfect wave fronts at which all the points on that wave will be in phase. So effectively, what that means mathematically is if you were to draw a line here, and if you were to look at this path length here, and this path length here, and this path length here, they'll all be equal. Okay. So what that means is if either you've got a planar wave incident on a parabolic antenna, it will all focus at the center, all in phase, or the reverse is if you put a transmitter at the focus of a parabolic antenna, it will produce a perfect plane wave. Now the next important thing associated with antenna is the concept of diversity. Now today actually when I'm talking to you, I'm talking to you through this mic, and this mic is connected to a little transmitter here, and this little transmitter talks to this box here, and this box here has two antennas. Okay, and the reason is you have some kind of diversity taking place, as you can see in this diagram here. Okay, so you've got two antennas being connected to a receiver, and the receiver is continuously looking at the signal that it is receiving from the two antennas. Okay, and it will select the signal that is best. Okay, so it will look at the signal from each of the antenna, and one thing it could do is something called switch diversity, where it takes the signal that is the largest output from these two antennas. Another type of diversity that happens is referred to as diversity combining, where it's essentially because the signals that are coming, for example, if I'm standing here, the signal that going to the first antenna will be slightly out of phase with the signal that is arriving at the second antenna. Okay, so you could have a receiver that could adjust the phase of the two signals and combine them together to produce a higher gain. Okay, and that is referred to as diversity combining, and that's used quite a lot if you have a 3G wideband CDMA phone. These techniques are implemented in those phones. Okay, and when we go to the 3G later on, we'll see more details about it. Okay, so diversity can be done in many ways. Okay, one thing is to have space diversity. Okay, where you separate in space the two transmission paths. In the when there used to be a lot of even now on microwave links between large cities, and sometimes these microwave links could be carrying all of the traffic between two major cities. Okay, you don't just want to have one link, because if that link was to fail, then you would lose all the all the traffic between those two cities. So sometimes they would have one set of antennas at the top, right at the top of the antenna, and maybe another set of antennas maybe halfway through, and that provides spatial diversity, because if one path was to be affected by different electromagnetic phenomena, the second path will be still operational. The other possibility is, instead of separating them in space, you can also have frequency diversity, where you might use one carrier frequency for one transmission and another carrier frequency for another transmission. So here you have frequency diversity. There's also time diversity. Time diversity is when you want to transmit any information between A and B, you are transmitting it a number of times, not just once. And even if at one particular time the signal gets corrupted, maybe at another period of time it won't. And in most of the spread spectrum kind of systems, especially the direct sequence spread spectrum systems, you see that the same information is being transmitted a number of times, and this is referred to as time diversity, where you are repeating the same information across time. So essentially all of these techniques are used to improve the performance, because at the end of the day you want to improve the performance of your wireless communication link that you are trying to build. The next point is about propagation models. How do electromagnetic signals travel between the transmitter and the receiver? Okay, now as time went on, we started on the lower frequencies and we moved up into the higher and higher frequency bands. So most of the lower frequency communication, frequencies up to about 2 megahertz, the electromagnetic signal can actually follow the contour of the Earth. Okay, and you can propagate quite a lot large distances using this. So for example, if you look at AM radio, okay, even sometimes when you go right into the bush, okay, where there is no antennas anywhere, you can still hear AM communication, because it's, especially at night, you get a much better signal. It propagates along the surface of the Earth much better. The second propagation mechanism is referred to as a skywave, because we've got this layer called the ionosphere well above the surface of the Earth, and this is an ionized layer, and any radio wave that is transmitted from one point from a transmitter will go up and down, keep bouncing up and down until it gets to the receiver. Now, sometimes those of you who have done amateur radio, these people are able, with amateur radio receiver, you are able to communicate with people who are on the other side of the planet, okay, using this technique. And in the olden days, I'm not sure if people still do it, but you used to have a lot of shortwave communication, and people used to listen to radio stations from the other part of the world using shortwave communications, using the skywave propagation mechanism. But as time goes on, as we move to high and higher frequency bands, we find out that line of sight of propagation is the only means of communication between the transmitter and the receiver. And so if you're looking at mobile communication or satellite communication, most of these, which are the higher frequency bands, rely upon line of sight communication. Okay, sometimes the electromagnetic signals can actually bend slightly as they go through the atmosphere, and you can get coverage beyond the horizon. So for example, if you've got an antenna here, even though the optical horizon is somewhere here, you can get radio coverage at some point beyond the optical horizon. This is because the electromagnetic waves, as they travel through the Earth's atmosphere, they get refracted, and you're able to get coverage slightly beyond that. Now, how do you use this information? Well, when you're planning a radio link, one of the important things that you want to know is how high should you place your antennas. Now, this is a very simple model. The models that are used in planning are much more complicated, but a very simple model states that the relationship between, if you look at the height of the antenna here, if this is the height of the antenna here, and this is this distance here, d, okay, the relationship between d, the distance between the antenna and the horizon, and the antenna height is given by this formula here. Now, there is a factor called K that is used, an adjustment factor, to account for reflection, and usually, now this can vary from one part of the world to another part of the world depending on the atmospheric conditions, because the way electromagnetic waves flow in the tropics will be quite different to the way they flow in colder countries, and very much different to the way they will flow in desert kind of conditions. So this each operator might use different values of K depending on the geographic locations. So, but a usual figure is K equals 4/3 that is used for this kind of. Now the question is, if you've got the Earth's surface something like this, and you want to put an antenna here and an antenna here, so that you can communicate between these. Okay, you can use the same formula. You call this D1, okay, and maybe you call this D2, okay, and you can obtain a relationship between the height of the antenna here and D1, and you can obtain a relationship between the height of the antenna here and D2. That's what they've done in the next case. So in the next case, if you know the maximum distance between the transmitter and the antenna for which you want to achieve a line of sight path, you could use this formula here to work out what are the heights you need at antennas at the two antenna sites. Now sometimes you might already have an antenna site on one site, so you might have to build an antenna site on the second site, so you can use this formula as a way of establishing what height you need. Now normally you have to, apart from taking this, I mean this is a very simple model, but there are other things that you also have to take in. You might have to consider the heights of trees that you have. You might have to consider something called Fresnel zone, which I'm not going to go into in this subject, in working out the exact heights of the two antennas that you need at the transmitter and the receiver. Okay, so when we start having, because we are more and more focusing on line of sight transmission path, line of sight transmission, there are different losses that occur. Okay, the first loss is referred to as free space loss. Essentially, any electromagnetic wave, as it's traveling through space, you have a certain amount of loss that occurs with distance, and we'll see that as we go to higher and higher frequencies, we have free space loss actually starts increasing. The other thing that happens is atmospheric absorption. Okay, now atmospheric absorption becomes quite significant as we move to higher and higher frequencies. So things like water vapor and oxygen start absorbing electromagnetic waves at high frequencies. And some of these have to be taken into account. For example, if you're planning a satellite link in the tropics where there's a lot of water vapor, you have to consider the amount of rainfall and the amount of water vapor into the planning of a line of sight transmission. The next thing that occurs is multipath. Sometimes you could have many different transmission paths between the transmitter and the receiver, and this can actually cause the received signal to be less than what it was. So that also has to be taken into account. Okay, so what we'll do is it's almost 7 o'clock now, so let's take a quick break, 10-minute break, and then we come back after that. Okay, let's get started again. Now, when we've got wireless transmission, let's consider the case we've got a transmitter at the center of this circle here, and imagine that this transmitter is transmitting a signal. Now we know that when the signal strength starts to decrease rapidly with distance. So there comes a point, so within this big circle here, the first circle that you see here is a circle that is referred to as the transmission range. So in this range, it could be a few kilometers. This is a range within, and it depends again on the transmit power and the antennas that are used, and also depending on the threshold of the receiver. You have a range, a distance within which communication is possible, two-way communication is possible. So that means the receiver, if placed within the circle, is capable of understanding what the transmitter is sending, and the communication can take place at a low error rate. We go a bit further, there is another range that is referred to as, so the second circle represents, between the second circle and the first circle represents a range that is referred to as the detection range. So in this range here, you can detect that a signal is being transmitted at this particular carrier frequency, but the signal level is so low that you cannot have any meaningful communication between the transmitter and the receiver. And then outside the detection range, you get a region that is referred to as an interference range. Now in the interference range, you cannot distinguish between the signal that is transmitted by this transmitter and noise that you may be observing in the atmosphere. So essentially what this means that in wireless transmission, every transmitter beyond a certain point becomes interference for other systems that are using the same frequency band. Now if you were to plot the received signal strength as a function of distance from the transmitter, you might get a plot that looks something like this. So on the x-axis we have distance from the base station, and on the y-axis we have signal strength measured in or the gain or loss of the signal in terms of dBs. Now you see that there is a wide variation of signal strength as a function of time, as a function of distance. And people have tried to develop different mathematical models to model the change in signal strength as a function of distances. And again, it depends where these measurements are performed. If you were to do measurements in an urban area, in a city environment where there are a lot of buildings, and in a rural environment, the way this variation will be different. So in general, the path loss model is a model that is used to represent the variation of received power as a function of distance, is given by this mathematical expression here. Okay, so the path loss is d to the power minus gamma, where d represents the distance and gamma represents a path loss coefficient. Now, this path loss coefficient can take values between 2 and 4. If you're in an open environment, an open rural environment, the gamma could be 2, whereas if you're in a dense urban environment, the gamma could be 4. So in a dense urban environment, the signal will deteriorate much quicker with respect to distance. Now this has advantages and disadvantages as well. In general, if you were to look at the power received and the ratio between the transmit power and receive power, they can be expressed mathematically in this form. In the case of if you had an isotropic antenna at the transmitter and you had an isotropic antenna at the receiver, the relationship between receive power and transmit power is given by this mathematical equation. And you can express this in terms of dBs, and usually there is something called free space loss. So free space loss is the ratio of the receive power. It should be actually the receive power to the transmit power. And if you put the equation that we had in the previous slide, this one here, if you put this in this expression here, you will get a term. So usually the path loss in dBs can be obtained mathematically using this equation. Okay, that's another way of expressing the same equation. Now this loss, this path loss, is also plotted graphically for different frequencies. So you can see that this is on the x-axis you have distance in kilometers, and on the y-axis you have path loss in dBs. So as we move to higher, if you look at the same distance, for example, if you look at a distance of 10 kilometers from the base station, the path loss goes up considerably as you go into higher and higher frequency bands. So essentially what that means is to overcome the effect of path loss at higher frequencies, we have to employ antennas with higher gains and other techniques to overcome the propagation loss. Now we saw a graph for earlier showing how different how the propagation, how the received power varies with respect to distance. So for example, in the case of free space, when that coefficient gamma was equal to 2, you would get a received power signal represented in this form as a function of distance. When you are maybe in an urban environment, maybe with lots of buildings, you might have a propagation coefficient of 3.5, and the received power can drop very quickly. So you can see that if you look at a distance of maybe something like 20 kilometers in a rural environment, and maybe in a dense urban environment, the received power can be there can be a large difference between the received power at the same distance from the transmitter. Another formula that's used also for another mathematical model that is used for representing the received power is the plane earth propagation model. Okay, so in this one, the received power, the relationship between received power, transmit power, gain of the receiver and gain of the transmitter is given by this. So you can see in this case there is a d squared and a squared there. So this gives you a d to the power minus 4 variation for the received power as a function of distance. Now these are the very simple models. Then there are also far more complex propagation models. There are models that are used for mobile communication. There's a model called the HATA model. These models are based on physics, and then there are other models that are based on actual measurements. So there are groups of people who go in various cities and in different environments, and they measure the signal strength as a function of distance from the transmitter, and then they try to build some kind of a model based on actual measurements that they have taken rather than the physics of electromagnetic wave propagation. And these models are used quite a bit. So for example, these you might have a planning tool. Okay, so for example, the first diagram that you see here is the output from a planning tool that is used to say you're planning a wireless LAN for this flow. Okay, so this is a flow in a building where you have many offices, and then you and then you know the types of material that is used for all these separators that you have between rooms. And if you had a good model like that, you could have a planning tool where you could place the wireless LAN access point there and see how the signal strength varies at various points in the room. Okay, so you can see that the signal strength is very strong in this region here, and the colors could mean different receive signal strength. So the yellow could mean a very high receive signal strength, the orange could be an average receive signal strength, and the blue and the black could be a very low signal strength. So for example, in these rooms here, you could have a very low receive signal strength, and you might have to place a second access point maybe somewhere here so that you can get coverage in this area as well. This is in the case of wireless LAN. In the case of 3G or any mobile network, you could start off with what looks like a city with where all the roads are and all the buildings are and so forth, and you might put if you already had an antenna at one of these locations, you might see, okay, what will the signal strength be if you had a transmitter at this point in time. And so you know that the coverage is approximately this area here, and then you might have to put another base station somewhere here so that you can pick up the users there, and then you might have to put another base station somewhere here to pick up users that are outside the coverage area. So these are whenever you use a planning tool, it will show you a graphical representation of what the signal strength is at various locations based on different models that it may use to do that. Okay, now in terms of wireless transmission, what are the transmission impairments that you have? Well, whenever you've got a transmitter and a receiver, we've already talked about attenuation that occurs due to the fact that an electromagnetic wave is spreading and you lose some of the energy associated with it. We have noise that affects it. We have atmospheric absorption. We have multipath. So all of these are phenomena that affect the received signal strength. Okay, so probably the most important one is fading. Okay, because in fading you have a sudden drop in signal strength, and we could have fading occurring at very specific frequencies. So it's very much a frequency dependent concept. We have shadowing when, for example, you have somebody with a mobile phone, they walk and suddenly they take a 90-degree turn around a building and they are now in the shadow of the base station. Okay, so that is another phenomena that affects radio wave propagation. Then you have others like reflection, scattering, diffraction, and so forth. But probably the most important one is multipath propagation, because if you are a receiver there and you might have, and that's a transmitter, you have a direct path and you also have a reflected path. And if these different signals arrive out of phase at the receiver, they could cancel each other. Okay, and you have to have a mechanism to overcome the effects of this. Okay, usually this multipath creates something called intersymbol interference, where this energy associated with one symbol sort of goes on to neighboring symbols and affects the performance of the system. Now, in terms of mobility, one of the things that happens when users are moving is that the characteristics of the signal change over time. Okay, so because especially when you are as you are moving, there are many different paths that you can have between the transmitter and the receiver, and this change in the signal paths can result in different fading mechanisms. And we have something called long-term fading and short-term fading that can occur with respect to time. Short-term fading refers to a rapid or quick changes in the received signal strength as a function of time, whereas long-term fading refers to reduction in signal strength that occurs much more slowly with respect to time. So these two phenomena occur due to different effects that may be happening. But the most important thing is the short-term fading is very much dependent on the velocity at which you're traveling. So if you are moving much faster, you are more likely to have far more short-term fading than if you were stationary. Okay, now as a result, the other thing that happens as a result of movement is something called Doppler shift. Okay, so imagine if this was a transmitter and it was transmitting electromagnetic waves equally in all directions. Whether you are somewhere here or whether you are somewhere here, you see that the electromagnetic waves are arriving at you at the same rate. Now imagine that if this source was moving at a certain velocity in that direction. Okay, if that was to take place, then a receiver here and a receiver here will be observing different frequencies. A receiver here would be seeing waves coming at it much more quickly than a receiver here. So the frequency that is observed by a receiver here would be much higher than one that is observed there. So this produces something called Doppler shift, and this has to be taken into account when we start looking at different fading mechanisms that can occur. Now, I also told you about atmospheric absorption, the fact that there's water vapor, there's oxygen, there's fog. All of these absorb electromagnetic waves. And for example, in the case of a satellite, it becomes quite considerable. And in the case of a satellite that's communicating with the Earth, as this angle here, the elevation angle decreases. So as we go this way, this angle is getting smaller and smaller. So if this angle is getting smaller and smaller, as we go in this direction here, this angle is getting smaller. So we see that the electromagnetic waves are traveling through a longer distance of the Earth's atmosphere. And as they travel through a longer distance of the Earth's atmosphere, there's more likelihood of absorption due to rain and atmospheric absorption and so forth. So for example, in planning satellite systems, they have to take into account effects of rain and effects of atmospheric absorption and so forth. And it's also dependent on the elevation of the satellite. Okay, so those are the main phenomena that affect wireless transmission. The next thing that I'm going to look at is multiplexing. Now, what is multiplexing? You must have done this at some stage in your life.
Sharing the communication medium.
Yeah, sharing the communication medium. And how is it done? Okay, different ways that it can be done. What I try to do today, I'm not sure how successful we are going to be. Okay, the next topic that we'll have a look at is multiplexing. Now, there are different types of multiplexing techniques. You can perform multiplexing in space. That's referred to as space division multiplexing. The next type is frequency division multiplexing, time division multiplexing, code division multiplexing, and currently in optical fibers they use something called wave division multiplexing. which is another form of frequency division multiplexing. So one of the important things that I'm expecting you to be able to do is you should be able to distinguish between the different types of multiplexing techniques and give examples of one of each, because these techniques are used quite a bit in wireless communication. Okay, so what is meant by multiplexing? Well, essentially what you have is between a transmitter and a receiver, which could be many kilometers apart, you have one transmission link, and this transmission link could have a very large capacity. So what we do is we take n channels at one end, maybe at the transmitter, and we multiplex them together at the transmitter and transmit it through the transmission medium. And when this multiplex signal arrives at the receiver, you have a demultiplexer which demultiplexes the signal into the n outputs which were transmitted together on the transmission medium. So this is multiplexing, and as I said earlier, there are different types of multiplexing schemes. The main reason we use multiplexing is essentially it is far more cost effective to transmit all these n signals on one transmission link rather than transmitting on n different links. So as far as multiplexing is concerned, we have 4 dimensions. There is a space dimension, there is the time dimension, the frequency dimension, and also the code dimension. So as we said earlier, the whole idea is we want to use share a transmission medium to transmit a number of signals, either using space division multiplexing, time division multiplexing, frequency division multiplexing, or code division multiplexing. Now the important thing is that whichever technique you use, you need to separate them and have guard spaces in between. So for example, if you're using space division multiplexing, this is one, S1 is being transmitted in this space and S2 is being transmitted in this space. We got to make sure that there is sufficient gap, guard spaces between these signals so that they don't interfere with each other. Okay, so let's look at frequency division multiplexing. So in frequency division multiplexing, we take the frequency band that is available. As I said earlier, frequency is a very expensive commodity in wireless communication, and we have to use it very carefully. So what we do in frequency division multiplexing is take the entire spectrum of frequency that is available and we break it down into smaller frequency bands, and we allocate a frequency band to each particular user. So for example, in this case here, user K1 is being allocated that particular frequency band for the entire duration of time. So you can see there are 3 axes here. There is the space axis, which is C. There's a frequency axis, which is F. The frequency axis is the one that has been subdivided into, in this particular case, 6 smaller frequency bands, and each one of these 6 bands is allocated to the 6 users that are available. Okay, so it does have some advantages and disadvantages. The advantage being that there is no need to have dynamic coordination because everything is allocated beforehand, and so everybody knows which particular frequency they're going to transmit on. So there's no need for dynamic coordination. And this has been the primary way of communication in the older analog mobile communication systems like AMS and so forth. The disadvantage of this particular technique is that you waste a lot of bandwidth if you are not transmitting data. For example, if you use a K1, it does not have any information to transmit, then that portion of the frequency band over time is not being used, and that could have been allocated to somebody else. So there is a bit of wastage of bandwidth associated. And the other aspect is that we could have a situation where user K1 could have a lot of data to transmit, and maybe all of the other users have very little data transmit. So if there was a possibility that K1 could get a larger portion of the spectrum, then that would have been a more efficient utilization of the spectrum that we have. So there's a little bit of inflexibility associated with frequency division multiplexing. The other thing is you also have to have good guard bandwidth in between the different transmissions. So if you can see that these bands that exist here are essentially guard bands that are used to make sure that one transmission does not interfere with the other. Okay, here's an example of how frequency division multiplexing has been implemented. Now this particular slide is not from the Schiller text, it's from Stallings, but essentially I put it here to demonstrate in reality how frequency division multiplexing is implemented. So you've got a number of users here. You've got user M1, you've got another user M2, another user M3, up to Mn. Each user is modulated by a carrier F1, and we'll talk about modulation shortly. So when M1's spectrum is modulated by frequency F1, the bandwidth, the spectrum of M1 gets shifted to that portion of the frequency band, which is centered around frequency, the subcarrier frequency F1, and the second signal's spectrum gets shifted to subcarrier F2, which is a modulating frequency, and so forth. So each of these bands are separated. There's guard bandwidth here, so that their spectrums do not overlap. And these signals are then combined together by the summer and transmitted as a composite signal. So the signal that is transmitted here is all of this. This entire signal is transmitted at that point there. And at the receiver, when the signal is transmitted and it arrives at the receiver, you have band pass filters. So for example, you might have a band pass you might have a band pass filter F1. So F1 will just pick up that group of frequencies there, and it'll filter out all of the other components, and then that the filtered signal is then demodulated with frequency F1, and it'll result in the original M1 signal coming out here. So this is how a typical frequency division multiplexing system will be implemented. The second type of modulation technique is called time division multiplexing. So here you can see that everybody transmits on the same frequency. So all the users are transmitting at the same frequency, but they're all allocated a portion of time. So for example, in this, as a function of time here, user K6 is transmitting first, then comes user 5, and then comes user 4, and so forth. Or you could also think of it the other way, that first user K1 is transmitting, then user K2, and then user K3, and so forth. So here basically everybody gets allocated a slice of time, and they transmit in that time. So we, as opposed to frequency division multiplexing, in time division multiplexing you're only using one carrier at any point in time, because everybody's transmission is transmitted on one carrier frequency. Now you can achieve a much higher throughput because you can multiplex in time many users' transmissions. The only one of the main disadvantages of time division multiplexing is it requires very precise synchronization between the transmitter and the receiver, so that you can separate the individual users' transmission. Okay, now when I talked about synchronization, essentially this shows a block diagram of a time division multiplexing system. So you've got each user's transmission. Essentially, we are dealing with digital transmission here. So a bunches of ones and zeros coming in here, going into a buffer, and here you have a scan operation here, which essentially takes, in the first time slot it may read 8 bits from M1, and in the next time slot it may read 8 bits from M2, and so forth till the end, and then it goes back and starts reading from M1. So the composite signal that is transmitted here is could be of this form here. Okay, so you may have, in the first frame you may have maybe 8 bits from the first user. In the second frame you may have 8 bits from the second user up to the end user. And at the receiver, this signal, this digital signal is then modulated and transmitted on a transmission line, which could be a wireless medium as well. And at the receiver, you've got to do the opposite. So first you've got to demodulate it, and then you've got to recover the individual signals from the signal that you transmit. So here you've got another scan operation, which essentially might take, in the first time slot, it might take the first 8 bits, the first frame, and put it into M1 and so forth. And one of the important things that this scan operation here and this scan operation here need to be synchronized, so that we make sure that M1, the frame that came out of M1, ends up going out on this output here. So that's possibly one of the disadvantages of time division multiplexing. Here's a well-known format called the T1 format, which is used quite often in telecommunication systems, where you've got maybe a 1-bit control bit followed by the 8 bits. Usually 8 bits is used for voice transmission. So on channel 1 you've got 8 bits from the first user. On channel 2 you've got 8 bits from the second user, up to 24 channels. So here you've got 24 voice channels being multiplexed, time division multiplex, and transmitted. And so every 125 microseconds we have 193 bits being transmitted. I'll let you figure out where 125 microseconds comes from. If you go back to your knowledge of telecommunication system, you know that the voice is usually considered to have a maximum frequency of 4 kilohertz, and if you sample that at 2 times, that gives you about 8 kilohertz, and 8 kilohertz works out to about 125 microseconds. Okay, that's using the Nyquist theorem. So you have to, within a time frame of 125 microseconds, you are transmitting 193 bits, and if you work that out, that should give you about 2 megabits per second. Okay, now it's also possible to combine time and frequency division multiplexing, as in the case of GSM. For example, in GSM, we're going to have a full lecture on GSM later on, but I want to demonstrate here how in GSM a combination of time and frequency division multiplexing are used. So here we've got a number of carrier frequencies. Okay, so each one of these corresponds to carrier frequency, and these ones here on this way here corresponds to instance of time. Remember, this axis is the time axis. So this could be time slot 1, this could be time slot 2, time slot 3, and so forth. So in this particular case, user 1, which is this user here, which is user K3. K3 is transmitting at this carrier frequency in time slot 1, and maybe on this carrier in another time slot, and on this carrier on another time slot, and so forth. So the user is not just transmitting on one time slot, at different instances of time, it is transmitting in different carrier frequencies. Okay, so this is a feature that is available in GSM, and it essentially provides better protection against frequency selective fading. So for example, if you do have frequency selective fading and this carrier frequency is wiped out, then you know that the time slots in these carrier frequencies will get through, and you'll be able to have communication between the two end parties. Okay, but again, it requires very precise coordination, because now we have to know the frequency hopping pattern that is used at both the transmitter and the receiver. You not only have to synchronize in time, but you also have to synchronize in frequency between the transmitter and the receiver. Okay, the next multiplexing scheme that has become very popular recently, it did originate many years ago during the after the World War II period, where they wanted to have coded transmission between the front lines and the military headquarters, and this technique is referred to as code division multiplexing, sometimes also referred to as spread spectrum. So in spread spectrum, each channel or each user transmits at the same frequency and at the same time, but each user is allocated different code. And one of the things that we have to ensure here is that the codes that are allocated to users have to have a mathematical property called orthogonality, and we'll talk a little bit more about that later on. So in this case, you can see in this diagram all the users K1 to K6, all transmitting on the same frequency band, and all transmitting at the same time, but each user is sort of separated with different codes. And a good analogy of this would be what is referred to as a party room. And in a party room, you might have people talking in different languages to each other, and they're all communicating with each other at the same time and on the same frequency band, or within the same space, but they're all able to understand each other. Partially one of the reasons is once your human ear gets tuned to a specific language, it stays locked to that communication. So in terms of its advantages, it's very bandwidth efficient, because you're using the same band for multiple users at the same time, and you do not require any form of coordination or synchronization necessary. The only coordination you will need to know is you have to know what the codes that are being used by a user, and it also provides some protection against interference and tapping, because unless you know the code, you won't be able to listen to the communication. Okay, so that's a little bit of multiplexing, and the next topic that we're going to cover is modulation. Modulation. Okay, so what is modulation, and what is the difference between multiplexing and modulation?
Changing the amplitude, frequency, or phase of the signal.
And why do we do that?
Because so that we can avoid interference with the signal.
Okay. Okay, you're quite right there, but there's an important point that you're essentially, when you have a multiplex signal, you still have something called a baseband signal. Okay, that's a signal that is at the naturally occurring form. Now, before you actually transmit on a wireless system, you've got to move it to a higher frequency band. Remember, I told you earlier that as time went on, we moved from lower frequencies to higher frequencies. As the lower frequency bands got more and more congested, we had to move to higher and higher frequency bands. So essentially, modulation is a process by which we transmit a signal at using a carrier frequency. A carrier signal has three important properties: the amplitude, the frequency, the phase. So we vary these three properties of a carrier signal according to the information that we have, so that we can transmit signals at a much higher frequency. So we are essentially shifting, in the process of modulating, we are shifting the spectrum of a signal from the baseband up to the radio carrier frequency at which we're going to transmit. Okay, so if you're transmitting at the VHF band, we will shift it from baseband to the VHF band. If you're transmitting at UHF, we'll have to shift it from the baseband up to the UHF band. The main reasons that we do it, as I said earlier, as we go to higher frequencies, we need smaller antennas. We can also use modulation as a means of moving a signal to a particular band in frequency, so we can do frequency division multiplexing and so forth. So there are many different, two important techniques for modulation. There are modulation techniques that are referred to as digital modulation techniques, and the older modulation techniques are referred to as analog modulation techniques. So the digital modulation techniques are the ones that we're going to focus in this subject. Essentially, the three main types of digital modulation techniques are amplitude shift keying, or ASK, which is also referred to as on-off keying. The second type is referred to as frequency shift keying, and the third type of digital modulation is referred to as phase shift keying. So in amplitude shift keying, we always start off with a carrier wave, a high frequency carrier wave. So in amplitude shift keying, when we have a 1 to transmit, because remember these are referred to as digital modulation techniques because we either transmit a 1 or a 0. So when we have a 1, we transmit a carrier, and when we have a 0, we don't transmit anything. In frequency shift keying, when we have 1, we transmit a carrier of one frequency, and when we have a 0, we transmit a carrier of another frequency. But both these carriers are still in the frequency band that we want to transmit in. The third type of digital modulation technique is and the more popular one is referred to as phase shift keying. So in phase shift keying, when we transmit 1, we transmit one carrier wave, and when we transmit a 0, we transmit a carrier wave with opposite in phase. Okay, so we transmit one of two sinusoidal signals that are 180 degrees phase apart. Now there are also other types of frequency shift keying. There's something called minimum shift keying, and that is used in GSM, for example. In this one, we essentially take a data signal. So in this particular case, if we have a data pattern that goes 1 0 1 1 0 1 0, we divide it into the even bits and odd bits. So for example, if this is 1, then it's 1 and 1 here. Where it's odd, it remains 0 and 0. So the even bits change at every even position, whereas the odd bits change at every odd position. And then there is associated with the even bits. So if the even bit is, so we have two particular frequencies. So if the even bit is 0 and the odd bit is 0, then we transmit a carrier of high frequency. So for example, here we have the even bit is a low, a 0, and the odd bit is a 1. So a 0 and a 1 will produce N, which is the lower frequency. So the low frequency is transmitted between those 2 points, and so forth. So you can work through this table. It's a truth table, so you have to find the value of the even bits and odd bits at each time slot and use this truth table to determine whether the high frequency signal or the low frequency signal is transmitted. So this is a slight variation of frequency shifting. Essentially what you're transmitting is either a high frequency carrier or a low frequency carrier, but it's done in such a way that there is no abrupt changes in the carrier signal that is transmitted. You can go further in phase shift keying. There are the one we looked at was binary phase shift keying. So again here this is the phasor domain. Now remember earlier we talked about the amplitude domain, the frequency domain, and the phase domain. So in the phase domain you would represent binary phase shift keying has two phases. Okay, this phasor corresponds to this phasor here corresponds to a phasor that is transmitted for a 0. This phasor here represents a phasor that is transmitted for a 1. So you either transmit this sinusoid or this sinusoid, and the two sinusoids are essentially 180 degrees apart. You can go further and say in QPSK or quadrature phase shift keying, you are transmitting one of 4 phases. So that's one phase there, a second phase there, a third phase there, and a fourth phase there. Okay, so these phases are 90 degrees apart. Okay, so think of 4 sinusoidal signals that are 90 degrees in phase apart. Now, depending on, you essentially group the bits that you receive into pairs. So, for example, if the first bit and the second bit are a 1 and a 0, you transmit this particular phasor. If the next 2 bits are a 0 and a 0, you would transmit this phasor, and so forth. Okay, so this is referred to as a quadrature phase shift keying. You can also have other phase shift PSK schemes like 8 PSK. Okay, so in 8 PSK, you've got, instead of having 4, you've got 8 phases. Okay, and 8 PSK is available in as a modulation scheme in GPRS. So you can, and edge, where you can get for every symbol. So in this case, every time you transmit a symbol, you are transmitting 3 bits associated with it. And you can start having more complicated phasor representation. So for example, in a diagram like this one here, if you look at this diagram here, you have 16 possible phases in the IQ diagram. So here you have some phases that are different in amplitude and some phases that are different in phase. So depending on the bit pattern that you receive, you transmit one of these 16 phase patterns. Okay, so you can get more and more complex phasor diagrams. Obviously, when the more complex the phasor diagram that you use, the more the bits that you are transmitting with every phasor. So essentially what it means is you are able to achieve a high data rate. So sometimes QAM is used in HSDPA technologies where you're able to get much higher data rates. Now sometimes in wireless communication systems, you might initially start off with a modulation scheme like QAM, where you're able to transmit maybe 4 bits per symbol. But if the transmission medium becomes very poor, then you might drop down to 8 PSK. And if the transmission medium gets even worse, okay, you might drop down to QPSK and down to BPSK. So the modulation scheme that is being used can change as a function of time based on the channel conditions. Because remember, the more noise there is in the system, the more likely the 2 phases are going to interfere with each other. Okay, the last thing that I want to cover today is SPED spectrum. Okay, and SPED spectrum, we talked a little bit about CDMA, and we are going to look a little bit more deeper into SPED spectrum. So what, maybe we should take a break now because you probably had enough. Okay, the next thing that we are going to look at, the last thing that we're going to look at today is SPED spectrum. Okay, now the idea behind SPED spectrum is to SPED spectrum essentially takes a narrowband signal and it spreads it, or it puts the signal across a very wide band of frequencies. Now, the main idea behind that is, even if there was some kind of interference, for example, if the blue portion here represents the signal, the spread signal that is transmitted, and even if a portion of this spread signal is wiped out by interference, which is shown in pink here, you see that the remaining part of the signal gets through. And if you can in some way duplicate the signal that you want to transmit across this entire band, okay, so that there are many copies of the signal that you want to transmit, and these are transmitted across this wide band of frequencies, even if a portion of that band gets wiped out, the rest of it gets through, and you be able to recover the original signal at the receiver. So that's the basic idea behind spread spectrum. Now, in some ways, it looks a bit wasteful because you're just transmitting the same information in a number of different across the frequency band. But in other ways, it becomes quite useful as a means of protection from narrowband interference, which is very common in wireless systems. Now, if this was the signal that you transmit, and at the receiver, at the transmitter, you spread the signal, and at the receiver, you despread, or you do the opposite of the spreading process. And in the process of despreading, your original, the spread signal becomes a narrowband signal at the receiver, and the narrowband interference, which was a smaller band, becomes spread over a larger band of frequencies. And you can distinguish between the original signal and the interference. So essentially what you're doing is taking a narrowband signal at the transmitter, spreading it across a wide band of frequencies and transmitting it, and at the receiver you are despreading it and you get back to the original signal that you are that is done. So it essentially provides a form of security as well, because if you do not know how the signal was spread at the transmitter, you're not able to despread it at a receiver. There are two types of spread spectrum technology. The first one is called direct sequence spread spectrum, DSSS or DSSS, and the second type is referred to as frequency hopping spread spectrum. And we'll have a look at these two spread spectrum technologies in the last part of this lecture. So as I said before, the first step, initially you start off with a narrowband signal at the sender at some power, and as a result of spreading it, okay, you're spreading the same signal over a wide band of frequencies. Now the power has to remain constant, or the area of this graph has to remain the same. So the power, the transmit power of the spread signal is much smaller. So in some ways you cannot notice the difference between the spread signal and interference. And then when you transmit it, this is at the sender, when you transmit it, you will have broadband interference and also narrowband interference being added to it. And at the receiver, because you are despreading it with the same spreading techniques that you use at the transmitter, you are able to get the high-powered original narrowband signal here, and which will be at a much higher amplitude than both the broadband interference as well as the narrowband interference. And you'll be able to use some kind of band filtering and recover the original signal. So this is a very simple way of denoting how spread spectrum works. Now we're going to look at more details about direct spread spectrum and frequency spread spectrum in this particular case. Okay, so let's look at what happens in direct sequence spread spectrum. So essentially what happens in direct sequence spread spectrum is that if you have, if this is your user data, so here you have say a 0 and then a 1, This 0 is essentially over a bit period, okay, of the user data. You are multiplying each user bit by something that is called a chipping sequence. So for example, this 0 here is multiplied by a chipping sequence which goes 0, 1, 1, 0, 1, 0, 1. Okay, and then the 1 is also multiplied by the same chipping sequence. So the chipping sequence that we're using in this particular example is an 8-bit pattern. Is it an 8-bit pattern? I think it's a 7-bit pattern. There's a 7-bit chipping sequence pattern which goes 0, 1, 1, 0, 1, 0, 1. Okay, so every bit, every binary bit that the user has is multiplied by this particular sequence. Okay, so the way, if this is your input multiplied by the chipping sequence, and this is the resulting signal that you obtain. Okay, so this is now you can see that if this was the original the original user signal, which would have been a narrowband signal, now we are transmitting a signal which is a much higher frequency signal because of the fact that you are multiplying it by the chipping sequence. Now in this particular case the chipping sequence is 7 bits, but you can have much larger chipping sequences. You can have 128. Most of the time it's powers of 2, so it can be 128, 256, 64 bits and so forth. Obviously the larger the chipping sequence, the higher the bandwidth of the resulting signal that you obtain. Now one thing that you will notice is you can see that in each of these chipping sequence the same information is being transmitted. So basically if this is the transmitted signal here, if you compare it with the chipping sequence, you can know that it was a 0. Essentially what you do is you take that signal and you XOR it. Now remember, I don't know if you remember, there are in digital electronics you have AND operation, OR operation, XOR operation. So this is what they have done is they have taken this user data and XORed it with the chipping sequence to obtain the output. So for example, a 1 and a 0 will produce a 1 and a 1 will produce a 0. Okay, so that's the XOR operation that is used for producing the output. Now the thing about the you'll notice that if for example there was some kind of fading that occurred, okay, when this signal is transmitted and these bits got wiped out. So imagine that these bits got wiped out in the transmission process. Now because the information is also contained here, okay, now by looking at these bits here and by comparing it with the chipping sequence, you know that what you transmit here was a 1. So essentially what you're doing is the same information is being transmitted many times, and you are able to, even in the presence of noise that wipes out quite a few bits, maybe a few bits got wiped out there, a few bits got wiped out here, you can still from the received signal you can still recover, you can know straight away by comparing the bits that are okay with the chipping sequence, you can know whether what was transmitted was a 0 or a 1. So essentially what direct sequence spread spectrum does is it, even in the presence of frequency selective fading, you can still recover your original signal, and hence it can provide, essentially what it does is it provides a better quality communication compared to the previous, the other multiplexing and modulation schemes that we've talked about. So what exactly happens at the, if you look at a block diagram of a direct sequence spread spectrum, you essentially take your user data and you multiply it by the chipping sequence. Now I told you the length of the chipping sequence can change, okay, in multiples of 2. Okay, usually it starts off with maybe 16. You can use a 16-bit sequence, a 32-bit sequence, a 64-bit sequence, and so forth. And as a result of multiplying the user data with the chipping sequence, you get the spread spectrum signal. And this spread spectrum is then modulated. Okay, and you can use different modulation scheme, QPSK, 8PSK, QAM, all of these different modulation schemes that we talked about earlier. And then it's transmitted, and at the receiver, the transmitted signal arrives at the receiver. You have to demodulate it with the same modulation technique that you used there, and then you again multiply. Okay, so essentially after you demodulate, you still have the spread signal, so you multiply it by the chipping sequence again to get the original signal. Now, if you notice, if you take this signal here, and if you take this received signal and you do an XOR operation with this signal, you'll find out you'll get exactly the same signal. So that is that's what happens at the receiver. At the receiver, you multiply the demodulated signal by the chipping sequence, and you're able to obtain the original binary data that you transmit. Now, for example, in UMTS, the chipping sequence is dependent on the user data rate. Okay, so for example, if a user is transmitting data at a very high rate, then you will use a smaller chipping sequence. And if the user data rate is low, you would use a high chipping sequence in such a way that the data rate that's coming here is a constant. Okay. The next type of hopping is referred to as, it's very similar to what happens in GSM, but it's referred to as, the hopping is done much faster, okay? And this is called frequency hopping spread spectrum. So essentially what happens here is you don't multiply, to achieve the effect of spreading, you're not multiplying by chipping sequence, but essentially what you're doing is, for this period of time here, you are transmitting the signal at frequency F5. For the next period of time between there and there, you are transmitting in this particular frequency and so forth. So you are essentially hopping the frequency, and you're hopping it's so fast that for somebody who is looking at the signal that is being transmitted, it looks as if the user is using that entire band of frequencies. Okay, now again, even in this case, if selective fading was to occur and a portion of the frequency band was to get wiped out, you will still be able to recover the original signal. So frequency hopping spread spectrum. The one that is more used in wideband CDMA is the direct sequence spread spectrum technique. So in frequency hopping spread spectrum, there are two possibilities. There is one that's called fast hopping. That means you do several frequencies per user bit. And the other one is referred to as slow hopping, where your carrier frequency is changing much more slowly with respect to the bit rate. Okay, so for example, here, this is an example where you've got user data 0, 1, 0, 1, 1 being transmitted. In the case of fast hopping, even within one user bit here, so between this and this point here, you can, if you look here, you can see that you initially transmitted at frequency F1, and then at frequency F3, and then at frequency F2, all for one bit. So so essentially what you're doing in this case, you are doing 3 hops for every bit, 3 frequency hops for every binary bit that you're transmitting, and so forth. So essentially what that means is, even if there was frequency selective fading and this frequency was wiped out in that time interval there, you still have the same information being transmitted at frequency F1 and F2 within that bit interval, and you can recover the original signal from that. Okay, so this is frequency hopping spread spectrum, where instead of multiplying your binary data with a chipping sequence, you hop your carrier frequencies, and so from the perspective of somebody who's observing the system, it looks as if the user is hogging up the entire band of frequencies. So again, in this one here, the block diagram of a frequency hopping spectrum will be taking your user data, you can modulate it straight away, and then the modulated signal is then multiplied by the hopping sequence. So the hopping sequence is fed into a frequency synthesizer which changes the carrier frequency, and your carrier user frequency changes from F1 to F3 to F2 based on the hopping pattern. Okay, so that's about all that I wanted to tell you about radio wave propagation. Now there's quite a lot of this is a big chapter, so there's quite a lot of reading for you. Okay, now if you look on UTS Online, if you look on UTS Online,